All right, today we are diving deep into something truly amazing, atomic spectroscopy. It's this incredible technique that lets scientists look at pretty much anything and read the unique signature of every single element inside it. I mean, just think about that for a second. How on earth can we possibly tell the difference between one single atom of gold and one single atom of lead? It honestly sounds like something straight out of science fiction, right? Well, that is the exact question we're going to tackle. And the secret, the key to it all, lies in this one simple but incredibly powerful idea. Just like your own fingerprint is unique to you and only you, every single element has its own spectral signature. It's a specific, one-of-a-kind pattern of light that it either absorbs or gives off. And that fingerprint is what lets scientists identify it with, absolute certainty.
So, if we're going to learn how to read these elemental fingerprints, we first have to get familiar with the tool for the job. So let's ask the big question. What exactly is atomic spectroscopy?
Okay, try to picture it like this. Every element in the universe is like a tiny, unique tuning fork. And when we ping it with some kind of energy, like light, it rings with a very specific set of notes. Spectroscopy is basically the science of listening to those notes. By analyzing the music the light an atom soaks up or gives off, we can tell exactly what it is. It's just a really beautiful and elegant way of investigating the world.
Now, you can't just point a machine at some random object and start reading its atoms. It's not quite that simple. There are some fundamental rules to this game, a few core principles that make this whole amazing process even possible.
First off, the atoms have to be in a gas state, kind of flying solo. That way, their individual signals don't get all jumbled up together. Second, atoms give us these incredibly sharp, distinct lines of light, not the messy, blurry bands you'd get from bigger molecules. That sharpness is what makes the fingerprint so crystal clear and easy to read. And finally, and this is really the magic of it all, each element's electrons live in their own unique energy levels. This means the light it emits or absorbs is its exclusive signature. No two elements share the same one, period.
So how does the machine actually pull this off? Well, you can think of it like a tiny obstacle course for light. First, you have the source, which shoots out a beam of energy. That beam passes through the sample container, where our free-floating atoms are waiting to absorb some of that energy. Next, the wavelength selector acts like a bouncer at a club, only letting the specific color of light we're interested in get through. Then, the detector measures exactly how much of that light made it to the other side. And finally, the signal processor takes all that data and translates it into the fingerprint we can actually read.
So we've got the basics set up down. But as you might have guessed, there isn't just one way to do this. Scientists have a whole toolkit at their disposal. Let's start with the most common category, optical methods, the ones that are all about reading those light signatures. Broadly speaking, there are three big families of this technique. Optical methods are kind of like identifying a bell by the unique sound it makes. Mass spectrometry is more like identifying it by its weight. And X-ray spectrometry, that's like taking an X-ray to see its internal structure. Each one tells you something completely different, but equally important.
Now, within those optical methods, there are two main approaches. With emission, or AES, you basically heat the atoms up till they glow, and then you measure the light they give off. With absorption, AAS, you do the complete opposite. You shine a very specific light through the atoms and measure how much of it gets soaked up. So one measures what's coming out, the other measures what's missing. Two sides of the same coin, really.
And this is where the technique becomes so unbelievably powerful, especially for emission spectroscopy. See, it's not just about identifying the element, it's also about counting it. The whole thing is based on a simple principle. The brighter the light an element gives off, the more of that element is actually in the sample. This lets you do incredibly precise quantitative analysis. But what if we want to go beyond just looking at light? What if we need a different angle? Well, that's where the other two major techniques come into play. And they offer different and sometimes way more powerful ways to analyze our sample. Mass spectrometry is a whole different animal. Seriously, forget light for a minute. This is all about weight. The technique zaps atoms with an electrical charge which turns them into ions, and then it literally flings them through a magnetic field. Now, just like a heavy bowling ball is going to curve less than a light tennis ball, heavier ions bend less than lighter ones. By measuring exactly how much they bend, the machine can sort them perfectly by their mass. It's so precise it can even tell the difference between isotopes, heavier and lighter versions of the very same element. And when you combine this with other techniques, the results are, well, they're just staggering. There's one method called ICP-MS that improves detection limits by 2 to 5 orders of magnitude. Now let me be clear, that doesn't mean 2 to 5 times better. It means 100 times better, all the way up to 100,000 times better. That is the difference between spotting a car from a helicopter and being able to read its license plate. It is just astonishingly sensitive.
And finally, we've got X-ray spectrometry. You can think of this one like a medical X-ray for an atom. It uses these high-energy beams to look deep inside, to probe the core structure. But its biggest advantage is that it's often non-destructive. You don't have to burn or vaporize your sample. And that is absolutely essential when you're analyzing something irreplaceable, like, say, the ink on an ancient manuscript or the metal in a historic artifact.
So, look, this is all fascinating science, for sure. But why does it actually matter to us in our daily lives? Well, it turns out this Atomic Investigators Toolkit is working behind the scenes every single day to keep us safe and to help us understand our world. I mean, it's being used right now to detect dangerous pollutants like lead in our drinking water. It helps geologists find valuable ores by analyzing rock samples. It makes sure the food we eat is free from heavy metal contamination. From clinical labs checking our health to factories making sure their products are pure, atomic spectroscopy is truly one of the unsung heroes of modern science and industry.
So the next time you look at a drop of water, a piece of metal, or even just the air you're breathing, just remember that it is filled with these tiny, invisible elemental fingerprints. And with the tools of atomic spectroscopy, we finally have the power to read them. The only real question left is, what other secrets are they just waiting to tell us?